Okay, thank you guys so much for coming to our last workshop. It's just gonna be the two of you, it looks like. But today we're going to cover recursion and dynamic programming. Okay, first off, we have a raffle from last week. Your name's Christoph. Can you remind me of your name one more time, just so I know? Samuel? Yeah. Cool. Okay, you guys are both on the raffle. So let's see, which one of you will it be? We're gonna get a lot of random people maybe. Hopefully this is fast. Oh, dang. Congrats, Christoph. Third victory. We'll have one last raffle for the contest this week that we will just do on our own. So don't forget to submit problems because we'll still do it. Okay. Another person? No. Yes. Ah, come on in. If you want to go to the slides to see like what links and everything we have, you can go to the link at the bottom of the screen and grab some candy if you want and get set up. So today we're going to cover recursion and dynamic programming. Hopefully you guys have maybe heard of these topics. So when we talk about recursion, we're going to use factorial and a palindrome checker as a couple quick examples. And we talk about dynamic programming, we're going to use the Fibonacci sequence and a two-tiling problem as our examples. And then we'll have 3 example problems for this workshop: Rijeci, anti-11, and the plank. And then we'll have a Kahoot. So what is recursion? I didn't add an actual poll here, but which of you have heard of recursion before? Just raise your hand if you are somewhat familiar with it.
Heard about it.
Heard about? Okay, cool. Well, we will go over it in depth. We'll just skip over the basic details. So recursion is defined as the repeated application of a recursive procedure or definition. And in computer science, what this mainly refers to is the operation of a function calling itself one or more times in succession. So this is a useful tool in a lot of problems, especially in competitive programming, because it allows you to solve a problem based off of the answer to subproblems. So if you can break down a problem into smaller and smaller, easier pieces, and then solve each of those steps recursively, then it is a great tool for solving an overall harder problem. And that's a quick code snippet to show you kind of what I mean by a function calling itself. So as to use factorial for an example, this is a kind of a basic, most basic recursion technique that you can use in computer science. So let's say you want to write a program to compute the factorial of an infinite n, where factorial is n times n minus 1 times n minus 2, and so on and so forth, times 1. If you wanted to use a for loop to do this, which is a perfectly viable approach, you could do it as such, where you just define a total equal to 1, and then you can either iterate from n to 1 or from 1 to n, and you multiply your total by each number in succession, and then return that number. This is a fine approach, but just to show you how recursion can be used instead, I just wanted to give that as an example. So can anybody tell me how we would go about implementing this using recursion? Just in like a sentence or a word.
We have to have a base case, which is n equals 1, which is return n 1, and then the recursive case is like n times factorial of n minus 1.
That was fantastic. You actually skipped the first step, which was I didn't add a base case. I was going to say what's wrong with this function, but yes, you got it perfectly right. You multiply your answer by n times the factorial of n minus 1. And make sure that you always have a base case, which is the point at which your recursion will stop. So in every sort of recursive function that you write, you always need to make sure that there's some point at which you end recursion so that it can return up the recursion call stack and get back to your initial call and give you your final answer. But yes, returning n times factorial n minus 1 is our main solution to using recursion for factorial. Now, if we were to write a palindrome checker, where a palindrome is a word that is the same forward as it is backwards, maybe just take a couple minutes and either jot something down or just think about the pseudocode for how you would go about doing this, given this quick snippet here, where you have a function that returns a Boolean of whether a given word is a palindrome or not. And I just set up this int length equals word.length, so you could use that as a variable in the function. So just take a couple minutes, think about it, and then I'll go over it. Sure. Okay, hopefully that was just enough time for you guys to get an idea about how you might go about solving it. Don't have to have any fleshed out solution. I will go over exactly what you do. But basically, for this problem, there are three main things that we're going to check for. We always have our base case and our recursive call, like usual. Our base case in this case is going to be if the length is less than or equal to 1, because if you have a word that has 0 characters, it's automatically a palindrome. If it has 1 character, then clearly it's the same forward and backwards. So now that we've established our base case, at which point we return true, we go into a condition check first. You can also do this after the recursive call. You can flip the order, but just to make it clear, this is what we check to make sure that the word that we are checking is still a palindrome. And if it's not, then we return false. And our check here is if the first and the last character of the word are the same. Because if the first and the last character are not the same, then clearly the word cannot be a palindrome, because if you flip it, they'll be different. So we check if word 0 is not equal to the word of length -1 and return false at that point. Otherwise, we return a recursive call to this palindrome function of every character in the word except for the first and last one. So effectively, what this recursively does is checks each first and last character until you make it to the middle, at which point you get your base case of either having length 1 or 0, depending on if you started with an even length and odd length string, and that will give you your solution. It will return true for any recursive call stack that reaches the end, and it will return false if it ever encounters a misalignment where you don't have the same character. Does everyone get that? Any questions? Okay, cool. So just to go over recursion as a concept in general, it's a technique for a function calling itself. For example, when we use factorial, we multiply n by a factorial of n-1. It must always include a base case to ensure that recursion ends. So this is when n is equal to 1 in factorial, or when length is less than or equal to 1 in palindrome checking. And as we saw in palindrome checking as well, you can also include a check or a condition to terminate recursion early and stop the process before you continue on unnecessarily. So if you ever determine that you've found an answer to your recursive function, then you can just return and recursion can finish at that point.
A quick question.
Yeah.
Like, say what if the answer you're looking for, like, it's possible it doesn't exist? Like, is there a case, like, how do you protect against an infinite recursion if, like, or would you just never want to be in the case where it might not end?
That is a major problem in computer science in general, which is dealing with problems that don't necessarily have answers. There's a lot of ways to work around it and trying to convert the problem into a form that will either have like a true or false answer. But typically you just do want to avoid that sort of situation. So only write a function if you know that it will terminate in every case. If it's not gonna, definitely end, then you gotta think of a way.
Might as well do a for loop or something.
Yeah, I mean, usually they'll give you some sort of problem statement in competitive programming that can be worked into a solvable problem somehow. So
I was talking in general, because I probably won't be doing anything competitive programming, but I do a lot of programming.
That's fair. Yeah, I mean, it's an ongoing topic of research in computer science about how to make problems solvable, essentially. So yeah, just try to avoid that if you can, because infinite recursion is common. Yeah. So as this last bullet point mentions, we only run into issues when recursion runs too deep or makes too many recursive calls, such as when there is no solution to the problem. So one of the ways that we can avoid this kind of issue where we're making too many recursive calls and our call stack is running too deep and we're using up resources and time of our program is through the use of dynamic programming. So have any of you heard or used dynamic programming before? No? That is perfectly fine. So dynamic programming, otherwise referred to as DP, is a method of breaking down bigger problems into smaller subproblems in which the results are reused, which is the key point here. So this is used when we can get the optimal solution by using the optimal solutions of subproblems to compute larger optimal solutions. So this is a similar concept to recursion, and it can actually be implemented through recursion or something similar to it. And some classic examples are the Fibonacci sequence, a knapsack problem, which you will encounter at some point if you ever take CS 180, and the Tower of Hanoi. So I know that's kind of vague, but let's just jump into an example with the Fibonacci sequence to explain what I mean by this. So hopefully you've seen the Fibonacci sequence before. If you haven't, it's basically each number is equal to the last two added together, starting with 0 and 1. It looks like that. So this is defined by a recurrence relation. As you probably are aware of, every number in the sequence is defined as the last two added together, which is a type of recursion, basically. So if we were to go through and find each number, you start with your two base cases here of the first number being equal to 0, second number being equal to 1, and then you run through, and for each F2 and above, you compute the value based on the last two. So f of 2 equals f of 1 plus f of 0, f of 3 equals f of 2 plus f of 1, and so on until as long as you need to go for. So we know that Fibonacci is defined by this recurrence relation. So take like 30 seconds and just think about how you would implement this using recursion. And it's somewhat similar to factorial. Okay, hopefully that was enough time just to think about it for a second. Again, we're just gonna, use these little exercises to get your brain thinking, but to go over exactly what you would do in this case, like the same as with factorial, we have our base case here where we check this time if n is less than or equal to 1, because we have two base cases of f of 0 being equal to 0 and f of 1 being equal to 1. So if n is less than or equal to 1, then just return it directly. And otherwise, we use our recursive call here twice to return the last two Fibonacci numbers added together. And this works in the same way that factorial would, except every single time that you compute a number, you're finding two recursive calls, which each branch out 2 times. So just to demonstrate what that sort of process looks like, we have our code snippet and our array on the right, which represent the Fibonacci sequence and our recursive function. And let's just go through quickly what sort of process your program goes through when it's computing these values. So if you're trying to find the fourth Fibonacci number, or F4 or fib of 4, the first thing your program does is check if it's less than or equal to 1. It's not, so it returns fib of n minus 1 plus n minus 2, which in this case is fib of 3 and fib of 2. The first thing it does is find fib of 3. So before it goes over to fib of 2, it calls fib of 3. Same process here. It meets the base case check, so it goes to the else, and it calls fib of 2 and fib of 1. So you get down to fib of 2, and then fib of 2 will call fib of 1 and fib of 0. But because these values do hit our base case, we just return them directly. So fib of 1 is going to be equal 1, and fib of 0 is going to equal 0. Now our fib of 2 call can finally return, is it has computed both of the values which it recursively called, and it gives us 1. And now we call our fib of 1 from fib of 3, and this one is directly 1, and we can compute fib of 3 finally, and now fib of 4 can continue on and call fib of 2, which is the second step in its addition process from the initial state. But we can see that we kind of end up going through the same process as before, where we get the 1, we get the 0, we compute fib of 2 equals 1, and then after that whole process, we can return fib of 4 equals 2 plus 1, or 3. So what do you notice about this structure here?
There are multiple function calls to this, like with the same parameter.
Yes.
Is like computing the same values multiple times.
Exactly. So we have this kind of identical tree structure here for fib of 2, where we are doing the same computation twice. So if we already had that value, things might be a little more convenient. Now, just to give you a fun little factoid, what the time complexity of this sort of process, the recurrence relation solution to the Fibonacci sequence, is actually 1.618 to the n, or the golden ratio to the nth power, which is pretty close to 2 to the n, which is one of the worst time complexities you can have in programming. So, for example, to compute fib of 100 would take around 30,000 years on a modern computer. Modern compilers can luckily recognize this and automatically fix it for you and make it faster, but there are ways that you can do that yourself as well. So it's a good thing to be aware of, because you don't want to have runtimes that are close to 2 to the n. So this is where dynamic programming comes in. If the issue is that we're computing the same value multiple times, then how can we fix this? Well, this is computer science. Why don't we just save the value of every item in a variable, and then for each index, store it in an array? Well, that is the very idea of dynamic programming. So for DP, we create an array of at least size, really n+1, so you can access the nth index. And for each recursive value that we compute, we are going to save it in our array at the corresponding position. So when we want to compute a new recursive value, like when we make a call to fib for a fib of 3, the first thing that we would do is just check if we already have that value in the array stored. And if it already is there, then we can just use that value since we already computed it. And if it's not there, then we can do the computation and set the array value accordingly. And then either way, at the end, we will just return the value at that array position. So that is the concept of dynamic programming, and we will go over it a little more in depth now. So one of the ways in which we can do this is through memoization, which is the use of creating this starting array. And then we basically do the exact same function that we had before, except now we do what I just said, which is checking the array position. If it's 0, aka like it's not set yet, we compute the value and then we return the value at that position. If it's already set, then we'll skip over that else, skip over all the computation that it entails, and just return the value directly. So can anyone tell me what the time complexity of this new solution is compared to the old one? The old one was O of 1.618 to the n. And this one will now be, don't have any ideas? Exactly, O of n, which is like a massive, massive time improvement. So instead of having this tree structure on the left, which will continue to exponentially grow and expand as you calculate higher values of fib, we are now only ever going to have to compute each value once, because once we have it, we store it in the array. And so the only thing that we have to do is for each value is one addition operation and one storing operation, which is O of 3 to the n or O of n. So we improve our time complexity quite a bit. So this is clearly a very important strategy, and it can also be applied to all sorts of other problems for a great time efficiency increases. Now there are two main approaches to implementing dynamic programming. The one that I just showed you, memoization, is kind of the more intuitive or recursive approach to dynamic programming, which is top-down. You recursively call your function in the same way that you would with factorial or Fibonacci, and in a way, this is starting from the original problem and working your way down through subproblems. Every time that you compute a value, you store it in the array, but you only compute them when necessary, when you need to use that value for a higher problem. The opposite approach is to use tabulation, which is to create an array from the bottom up. So we create our same array of storing each of the optimal solutions, but this time we just go from the beginning all the way up to the value that we want to compute. So we know that at some point, almost guaranteed, especially for problems like Fibonacci and factorial, you're going to use every single array position. So it might just be faster and maybe more convenient to start at I equals 0 and go until I equals n and just compute each value, knowing that once you get to I equals 4, for example, you already have array position 3 and 2 defined, and you can just use them directly. So those are two approaches to implementing the strategy. Okay, to give you a more in-depth example about what this really means, I gave you two functions here. One of them is our top-down memoized approach, which we had from before, and the other one is now a tabulated bottom-up approach. So you can look at it, try to understand a bit what's happening. The main thing to point out here is that for tabulation, you just start with your base cases directly. You literally set the array values to their base cases, and then you go from 2 to n, and you set each value to its corresponding value and return the last position. Whereas on the left, you're doing this recursive function where you're calling it self. Tabulation does not really involve recursion. So if you're calling fib of 5, for example, in order to find the 5th Fibonacci number, you're basically asking what is this position at the array? And with memoization, you would then work your way down. So calling fib of 5 would then call fib of 4, which would then call fib of 3, which would then call fib of 2. And then you'd get to your base cases 1 and 0 and work your way back up. On the other hand, if we go back here, we can see that with tabulation, when you call fib of 5, you immediately just start working from 0 up to 5. So you go to 0, you set it to your base case value. You go to 1, you set it to your base case value. And then for every other I up until n, you just set it equal to the Fibonacci formula. You add the last two array positions, and you work your way up until you set 5, and then you return the value of 5. So you can see that memorization is called top-down because it goes down through the array and then works its way back up the recursion, whereas tabulation just goes from the bottom, computes every value, and then returns the solution at the end. So our overall thought process here for solving these kinds of problems is to first figure out the recursive relation between optimal solutions and their subproblems. So, for example, in factorial, if you want to find 5, you got to find 4, and then 3, and then 2, and then 1. These are all subproblems of finding the factorial 5. And you can either iteratively or recursively, which are in reference to using tabulation or memorization, call the next subproblem and save each optimal solution in your array. And then at the end, you can return this optimal solution at your desired index n. And you also have to determine your base cases and implement them. So to jump into another example problem, this time you guys can try it out a bit more yourselves. This is going to be two-tiling, which is in how many ways can you fit a 2x(n), can you fill a 2x(n) rectangle with 2x1 dominoes? So that means that each of these little 2x1 dominoes you see here can either be vertical or horizontal like this. And the question is, if it's length n, how many ways can you arrange these dominoes uniquely? So we're going to let S of m be, or refer to the number of ways to fill a 2x(m) rectangle with 2x1 dominoes. And in our base case, if we have a 2x0 length plank or whatever, there's one way to fill it, which is to put nothing. And from this base case, we can extrapolate that each domino we place in a new configuration is either going to have to be these two stacked horizontal ones at the end of some other previous arrangement of dominoes, or one vertical domino at the end of some other unique arrangement. So I know that's a little bit confusing, but just to directly explain what that means, if you have a plank that's this long and you want to figure out the number of ways to uniquely add one more links to that plank, you can put a vertical plank at the end, or you can remove the last vertical plank and put two horizontal ones, which is basically to say that to find the number of ways to fill this plank, you take one that's two shorter, and you imagine that you added two horizontal dominoes to it, and you take one that's one shorter, and you imagine that you put a vertical one at the end. So that's one way, and one way to add on to these planks that are two shorter and one shorter. So that is to say that to find the ways to fill this plank, you need to find the number of ways to fill one that's two shorter and one that's one shorter, and just add them together. So we basically end up with the Fibonacci sequence. Surprise, surprise. So here's our little code snippet or starter code. Take maybe 2 or 3 minutes and just see if you can potentially implement this. Test it out on a couple input values like 5, 10, and see if you can get it to compute the right solution.
Unfortunately, we have to cut out, but I was just here on behalf of the startup and just wanted to hand out our cards in case we're looking to hire engineers. So
cool. Yeah, we're just looking to see what's the best way to connect with ACM for internships. We set a couple of stop limits. Nice. I want to see what you guys are doing.
Awesome. Thank you for showing up.
Yeah, really good class. I enjoyed it.
What would a good way to be just reach out directly by email, or how would you? Because I just assume you have quite a few computer science students.
Yeah, I mean, if you want to just contact ACM, there's always a ton of people who will be checking their emails and Slack and whatever, and ICPC is one of our subcommittees. Or you can reach out to any of our officers if you can find their information online. Cool. Yeah.
Okay. Yeah. Thank you very much.
Yeah. Thank you guys for coming.
Feel free to get those out for each of us.
Yeah. That's good.
On-demand waterfront storage terminal services.
Cool.
Yeah. Thanks.
Okay, hopefully you guys were able to come up with something. Doesn't necessarily have to be a fully working solution. Unfortunately, this problem is not on Caddis, so you can't submit it. But let's just go over quickly what the solution or a potential solution would be. So this is the tabulation approach. You could have implemented it using memoization, but honestly, 9 times out of 10, tabulation is going to be a more simple to implement and effective approach. So we start with a couple base cases here, where if you have a 1 long block, the only way you can fill it is with 1 vertical tile. If you have a 2 long block, the only way you can fill it is either with 2 vertical tiles or 2 horizontal tiles. And then our tabulation approach is just to, for each I from 3 until M, set the array position equal to the array of I-1 and of I-2. So hopefully now you understand the approach of how we do recursion, things like the Fibonacci sequence, and how we would implement dynamic programming in order to speed up the computation time. So now I will hand it over to Jason for our first example problem, Rijeci. You can go to the contest link right here.
Yeah, so feel free to join the Caddis contest. So for our first problem, we start out with the letter A, and every time we press the button, A becomes B and B becomes BA. And so we're trying to find out how many letters A, how many letters B will be displayed after pressing the button K times. So feel free to give it a few minutes to try to work out a solution, and then we'll go over the solution. So as Carson explained, with every dynamic programming problem, we want to identify the base cases, the recurrence relation, and then eventually implement the recursive process. So in this case, our base case is when we start out, we have a string that's just A. So our number of A's is 1 and our number of B's is 0. And after we press it 1 time, the A becomes a B. And so we have 0 A's and 1 B. And then can you guess, after pressing it again, what do we get? Well, the B just becomes a BA. So we have 1 of A and 1 of B. And then we can notice this pattern where as every time we press it, the number of A's becomes the next Fibonacci number. And the number of B's becomes the next Fibonacci number that's after A. So for example, the number of B's is 1, 1, 2, 3, 5, 8. Which are the first 7 Fibonacci numbers. And so our conjecture is that after pressing the button n times, we have f of n minus 1 A's and f of n B's, where f of n is a Fibonacci number. So our initial state is A of 0 equals 1 and B of 0 equals 0. And so what happens when we press the button? Well, we know that all A's become B's and all B's become BA's. And so from this, we get the relation A of n equals B of n minus 1. And what about the number of B's? Well, the number of B's is just the number of A's plus the number of B's. And so we get B of n equals A of n minus 1 plus B of n minus 1. So for example, here's a nice little graphic. Suppose that we have BA, BB, AB, AB after 5 button presses. Then after pressing the button 1 more time, we notice that each B becomes BA and each A becomes B. And so this is our string after 6 button presses. Oops. And so we notice that A of 6 or A6 equals B of 5 and B of 6 equals A of 5 plus B of 5. And so our conjecture is that A of n equals B of n minus 1. And B of n equals A of n minus 1 plus B of n minus 1. So we notice that since B of n equals B of n minus 1 plus B of n minus 2, and our base cases are exactly the same as the Fibonacci sequence, we know that it's just going to be the Fibonacci sequence, right? So B of n equals f of n. So yeah, we have our base case is A is equal to 0, B is equal to 1. And then for I between I and the number of presses, we're going to increase B by A, and then we're going to set A to the old value of B. And so this is exactly how we calculate the Fibonacci sequence. So yeah, that's essentially that problem. Any questions? Okay, cool. Then we'll move on to the second problem. And I'll hand it over to Carson.
Okay. Our second example, if you can go to the contest and click on the link for ANSI 11. Take like 1 minute just to read the problem statement quickly. Problem is basically given a integer n, how many substrings or how many strings of length n do not contain the substring 11 when converted to binary. So let's start off with our kind of base case here, which is our strings are always going to be of only ones and zeros. And for length 1, we have our two choices of 0 and 1, neither of which contain the substring 1, 1. When we go to length 2, we can either append to 0, a 0 or 1, or append to 1, a 0 or 1. And this gives us 4 options from our 2, one of which does contain the substring 1, 1, as it is that. So we know that we get one unusable string from this iteration. And then when we go to n equals 3, we do the same sort of operation where to 0, 0, we add a 0 and a 1, to 0, 1, we add a 0 and a 1, and so on and so forth. And we end up with these 3 substrings which contain a 1, 1. So is there anything that you can tell me about this pattern which identifies what situations we should avoid?
What do you mean, like,
Like when we increase the length of the string by 1, what operation causes these red cells to appear?
well, if we're adding 1, like just the cases when we're like adding 1 and there's already 1, like if we're adding 0, then like always like nothing bad happens.
Yeah, pretty much exactly that. It's just when we're adding a 1 to a 1 at the end. So from any given length, we can always attach a 0, giving us 2 new cases, but we can only attach a 1 given that the last character of the string before it is a 0. Because if it's a 1 and you add a 1, then you end up with something 1, 1. So that's basically our solution to the problem in more or less words, where we start with a string of 0 that has 0 options, and then we get to a string of 1, which has 2 options, and you can keep building that up until you get to length n, where you can append a 0 or a 1, and you can only append a 1 given that the last string ends with a 0. So take a few minutes and see if you can write out the solution. Wait, did we get started quickly? No. You got this. So in this case, our solution involves having 2 arrays. Normally where we have like just 1 for Fibonacci numbers, because we're always just pulling the last 2 values. On this one, we're trying to keep track of when our strings are ending in 0 or when they're ending in 1, because it's important to the problem specifications. So we set 2 base cases here, which are the number of strings of length 1, which end in 0, and the number of strings of length 1, which end in 1, both of which are clearly 1 from our base case from before. And then to do the tabulation approach, we take our 2 base cases, and then we go from I equals 2 to n. And for each one, here, it actually might be easier to explain with the image. For like setting the array position at n equals 2, for example, the number of ones that ended in 0 will be equal to the number of ones that ended in 0 before, plus number of ones that ended in 1 before. Because like you said, you can always add a 0. So you can just take the 2 array locations from before, imagine you added 0, and then set that to your current value of ones that end in 0. And then for ones that end in 1, you can only do it if the last one ended in 0. So you just take the last value of ones that ended in 0 and don't add the ones that ended in 1. So that's essentially our implementation here. You set the one that ends in 0 at I to the ends in 0 of I minus 1 plus and then 1 of I minus 1, imagining that you're putting a 0 on the end of all those previous strings. And then for ends in 1, you set it equal to ends in 0 minus 1 because you can't add it to anything that ended in a 1 before. And then as our final solution, we just return both of them added together, because that would give us all of the possible binary strings, which whether they end in 0 or 1 don't have the substring number. Does that make sense?
Yeah.
Okay, cool. We have one last problem, which is our like bonus problem. Do you want to do it?
Sure.
Sweet. Okay.
Alright, so the plank. So in this problem, we have three kinds of wood. We have wood of length 1, 2, and 3. And we're trying to find how many different ways we can glue together those pieces of wood to get a plank of length n meters. So give it a few minutes and try to think about it, and then we'll cover the solution. Okay, so hopefully you've had some time to think about it. So for example, let's say n was equal to 7, then we have, or sorry, let's say n was equal to 4, then you have all these different ways to make a plank of length 4. So for example, you could glue together 4 pieces of length 1, or you could glue together 1 piece of length 2 and then 2 pieces of length 1. Another thing you should notice here is that order does matter. So for example, you have that the plank in the top right, which is 1, 1, and a 2, is different from the one second down on the first column, which is 2 and then 1, 1. So yeah, order does matter. So we know that rearranging the planks is a new way. We also know we have an unlimited number of each type of plank. So also equal length planks are counted as 1. So for example, if you had n equals 2, then 1, 1 is the same as 1, 1. So our base cases are when n equals 1. So when n equals 1, do you know how many ways we can make?
It's just one way.
Yeah, exactly.
1 meter for one line.
Yeah, exactly. So when n equals 1, we only have one way, which is just a plank of length 1. What about when n equals 2?
That's 2 ways, either a plank of length 2 or 2 planks of length.
Exactly. And what about length 3?
4 ways. So it's either 3 planks of length 1, or it's just a plank of length 3. And then it's 2 planks of length 1.
Yeah, you're right. So it's 3 planks of length 1, or we could have 1 length 2 plus 1 length 1, and then we can swap the order, or we could just have 1 plank of length 3.
Oh yeah.
So yeah, exactly. It's 4. So these are our base cases. And do you see a way that we could construct, for example, n equals 4 from n equals 1, 2, or 3?
Yeah, so basically how I thought about it was like if we're like doing n equals 4, it's either like adding a plank of length 1 to n equals 3, or adding a plank of length 2 to like n equals 2, or like adding a plank of length 3 to n equals 1. So it's basically just the sum of like the number of ways we can do it for like n minus 1 plus n minus 2 plus n minus 3.
Yeah, that's exactly right. Just like you said, we have our base cases, which we just went over, and for our iteration, we just do the number of ways of I is number of ways of I minus 1 plus I minus 2 plus I minus 3. So yeah, just like you said, it's just the sum of the number of ways to do it for like I minus 1, I minus 2, and I minus 3. So yeah, that's the problem. Feel free to fill out our feedback form. This is the last workshop of the quarter, so we'll try to use the feedback for next quarter. And yeah.